This exercise 101B is an extension of exercise 101A, where we now perform a 3D finite element analysis of the same rectangular plate under static loading. The setup remains similar. A plate of dimensions 100 millimeters length into 40 millimeters width into 3 millimeters thickness is subjected to a 40 kilonewtons load applied in the x direction at the free end, while the opposite end is fully fixed. Unlike the 2D shell model used in 101A, this exercise uses a solid 3D model. In step 1A, we begin by creating the 3D geometry of the rectangular plate using FreeCAD. This is a transition from the 2D shell model in exercise 101A to a full solid model for 3D finite element analysis. Using the part design workbench, a new sketch is created on the XY plane representing the plate's face. The sketch is dimensioned as 100 millimeters in length and 40 millimeters in width. Once the sketch is complete, click Close to exit the sketching environment. Then proceed with the pad operation. The pad tool, found in the part design workbench, can be accessed in two ways, either from the toolbar at the top of the screen or from the modeling tools panel on the left side of the interface. After selecting the Pad tool, the Pad Parameters window appears. Here, the length field specifies how far the sketch will be extruded to form the solid model. In this exercise, a value of 3 millimeters is entered to represent the plate's thickness. This completes the conversion of the 2D sketch into a 3D solid plate. The model is then exported as a step file. In this step, the 3D solid geometry created in FreeCAD is imported into PrePoMax for further analysis, using the File Import option. Once imported, it appears in the Geometry tab as Solid Part 1, as shown in the left panel of the interface. In this step 2, the mesh is generated for the imported 3D solid model. The process begins by creating a mesh setup item and selecting meshing parameters as the type. Within this setup, mesh size controls are defined with a maximum and minimum element size both set to 4 millimeters, and 2 elements per edge and 2 per curvature are specified. Following this, a transfinite mesh type is selected, which is suitable for generating a structured hexahedral, brick, mesh, and the recombine option is enabled to ensure that the elements are converted from tetrahedral to hexahedral where possible. Then mesh is created by choosing the Create Mesh option from the Mesh drop-down menu. The result is a clean and uniform brick mesh. Next, node sets are created to define the boundary and loading regions of the 3D solid model. A node set named Fixed is assigned to the left face to simulate the clamped boundary, while another node set named Load is assigned to the opposite face, where the 40 kilonewtons force will be applied. In steps 2C and 2D, a reference point is created, and a rigid body constraint is applied to the load face of the 3D model. This step defines the material properties for the 3D solid model. Young's modulus of 72,390 megapascals and a Poisson's ratio of 0.33 are entered. In this step, a solid section is created and assigned to the 3D geometry. The previously defined material, Material 1, is selected for this section, and the entire part is chosen as the region to apply it. In this step, a static step is created to define the type of analysis the solver will perform. This step sets up a history output to track reaction forces during the simulation. A node output type is selected, and the variable to output is RF reaction force. The region is defined using the previously created node set named Fixed, which represents the clamped edge of the model. A fixed boundary condition is applied to the node set named Fixed to restrain all degrees of freedom at the clamped edge. Then a concentrated force of 40,000 newtons is applied in the x direction via the previously defined reference point 1, which is linked to the opposite face using a rigid body constraint. Once all setup steps are complete, the analysis is ready to run. Right-click on the analysis item, here named Analysis 1, and select Run. Upon completion, you'll see a status window showing details like the total time taken and convergence status. Click on Results to proceed to post-processing and visualize displacement, stress, and other output data. In step 6A of post-processing, we review the reaction force at the fixed end of the plate. Under the History Outputs section in the results tree, navigate to RF1 for the fixed node set. The output confirms a reaction force of minus 40,000 newtons, which matches the applied load in the simulation, but in the opposite direction. In step 6B of post-processing, the displacement results are visualized by selecting DISP All under the field outputs. The plot shows the distribution of total displacement across the solid plate. The maximum displacement observed is 0.4535 millimeters, located near the free end of the model, where the 40 kilonewtons load was applied. This result aligns with expectations for a fixed free setup under axial loading. In step 6C, the von Mises stress distribution is reviewed under the stress Mises output. The selected node at the center, identified using the query tool, shows a stress value of 335.1 megapascals and is located near the mid-region of the plate. Here, the strain distribution across the 3D plate is visualized using the E11 component under the toss strain field output. A node near the center of the plate has been selected using the query tool. The highlighted result shows a strain value of 0.004625. At the end of this exercise, the results from the 3D finite element analysis are validated by comparing them with the expected theoretical values for a simple tensile loading case. Using the given geometry, material properties, and applied 40 kilonewtons axial load, the analytical values for stress, strain, and elongation are calculated. The simulation results, such as the maximum von Mises stress, axial strain, and displacement, match closely with these hand-calculated values.